So in the last class we finished job scheduling. We gave this very simple implementation with a very creative idea and proof which takes order and log n time and is the number of jobs. So now we have to do this second problem, which is spanning tree computation. So you are given a communication or road or transportation network, and what you want is to find a spanning tree which is of minimum weight. Okay, so in terms of road, it is the distances, some of the distances you want to minimize. So it's an optimization problem. So input is undirected graph, edge weight function W, integral weights, and the output has to be a spanning tree G prime such that if you sum up the weights of the edges, it should be minimum possible. Any questions till now? Okay, so brute force is finding a subset, so that's very expensive, exponential in n. So how do we do it faster? So for this we'll use this idea that in a spanning tree, if you add an edge, then you get a unique cycle. Okay, so starting with this basic property, we want to design a greedy algorithm. Okay, this will be again be a great example of greedy paradigm. So shall we pick the min weight edge E0? Okay, since we want to find a minimum weight spanning tree, maybe we should start with picking the smallest road possible, right? So the minimum weight edge, let's call it E0. So let's keep an example in mind. So the weights are 13, 30, 52, 50, 33, 80 and 44. Here the minimum weight edge is 13. Right, so this is your graph. And these are, say, the vertices are cities, the edges are roads. So in this, the minimum weight edge in this graph is 13. So we want to do something with 13, right? So we pick that edge, and we say that, well, this has to be in the minimum spanning tree. So the question is this a correct assumption? So we'll now prove that it is actually correct. So we'll prove a lemma, like we did in job scheduling, that this greedy choice that we are making without looking at other aspects of the graph, we are just picking the min weight edge. This already is actually a good idea. We'll show that there exists an MST, minimum spanning tree. So maybe I should define that somewhere here. So we call this MST. Okay, so the question is computing the MST given a graph with weighted edges. So the lemma here will be that there exists an MST T of the graph G containing E0. How do you show this? So in this graph, minimum fit is 13. How do you show that there is a MST containing 13? Or in other words, starting from 13, we can incrementally build a MST, a spanning tree which is minimum weight. Any ideas? No, but this is just one edge. How can one edge form a cycle? So formally what you have to do is what you did in the job scheduling case. Similar lemma was there. Right, in the morning you saw that this lemma 1, there also we claim that there exists an optimal solution with this x. So we started with some s prime which did not have x, and then we transformed it so that it contains x, but is of the same size. So we'll do the same trick here, which is a completely different problem now. So consider another MST, T prime, without E0. Okay, so now what do you want to do there? In T prime, you want to pick some edge and replace it with E0, such that it continues to be an MST. So let us try to first add before deletion. Let's add. So let's introduce E0 in T prime. What happens? In a spanning tree, when you add an extra edge, what happens? You get a unique cycle. So this gives the cycle C. Using E0. Now you want to do something with the cycle and E0, right? You wanted to remove an edge and add E0. So E0 you have already added. What should you remove so that the cycle is gone? Well, in the cycle you pick some edge and delete it. That's all. So if this is your E0 and this is your cycle, then you just pick any edge, arbitrary edge here, and then you exchange them. In the sense that, well, E0 is already there, you just delete E and see what you have got. So swap, so let E be an edge, let E be an edge different from E0. And then delete it. To get T, a new graph. Now the question is that this new graph which you will get when you delete E, will it be a tree? Yeah, so here you do that exercise from the previous class where we observe that in a tree, if you add an edge, there is a unique cycle involving, and it involves obviously the new edge. So, so that C is the unique cycle. If I delete one edge from there, then the cycle is gone. So you are back to a tree. So when you delete E, then you get a spanning tree. Okay, so that's the major observation which you have to be convinced with. That exchanging E0 with a cycle edge gives you a new spanning tree. All that remains is weight comparison. What is the weight of T prime and what is the weight of T? So how do you compare weight of T with weight of T prime? Well, we can write down exactly actually. So weight of T is in T prime I have removed E0. Sorry, added E0 and removed E. Right? So weight of T is exactly this, removing E and adding E0. So which is what? E0 was the minimum weight edge. Right, this was the assumption. So since E0 is minimum, what you are adding to the weight of T prime is negative. I mean, it's less than equal to 0. So this is less than equal to weight of T prime. Fine. So if T prime was an MST, then T is also an MST. And additionally, it has E0. Is that okay? So just like the job scheduling lemma, we now have proved a lemma for graphs, whereby a similar idea, we can do the greedy choice, make the greedy choice of minimum weight edge. And you will be right. There will be some way to grow it to an MST. So then 13 we have picked. What should you pick after 13? So 13 covers these two vertices, right? These two vertices get covered. But there are still other 4 vertices which we need to cover, so we should do what? So that step you have to think about what to do, right? So let's try to develop this into an algorithm. This is not immediate, but you will see how it works. So that's the next question. What is the next step? To get the full MST. So we'll develop this next step using 2 different ideas. We'll get 2 different algorithms. In fact, this MST problem is a very useful problem in practice. So there are many old algorithms available based on many ideas. So in this course, we will pick only 2 ideas and we'll see 2 algorithms. Okay, so one of these algorithm is actually almost 100 years old. So we'll see algorithms based on 2 properties. So the first property is greedy by cut. Okay, so this for sure you would not know what a cut is in a graph. So we'll define that, and then based on that, we'll give you the next step. So once you have picked the minimum edge weight, minimum weight edge, E0, what should be the next choice to get towards MST, some MST. So this decision making will be done via this cut property. So let us define that. What's a cut? So for a subset A of vertices, cut is basically the A is a set of vertices, A complement are the remaining vertices. What are the cross edges? Okay, the cross edges from A to A complement they comprise the cut. So U is in A and V is in A complement. It's anyways an undirected graph, so V can be in A and U can be in A complement, same thing. Okay, so for example, you may have a situation where you are looking at a subset A of vertices, A complement is the remaining ones, which is V minus A. And so remember that this may not be a bipartite graph. So within A there are also edges. And within A complement also there may be edges in general. But the cut is interested in the cross edges. So like this edge is important. So this one with maybe weight 10. This one with weight 12. And this one with weight 9. Okay, so these red edges are the cut edges, the orange edges, we don't care. They are within A or within A complement. So cross edges, they are said to be the cut of A. So our next choice, what edge to pick will be dependent on this cut property. So what we will show is the following. Second lemma. Okay, again you can compare with job scheduling. So in job scheduling also we had lemma 1 was to give your strategy for greedy algorithm. So strategy was that you will take the earliest finish time, call that X, and then remove everything that overlaps with it. Right? And then lemma 2 was relating the big instance with the small instance. So similarly here now, in the MST problem, lemma 1 is to give you the greedy strategy that you want to start with minimum weight edge. Lemma 2 will be about what to do with the smaller instance. In fact, how do you even define the smaller instance? Right? So can you guess what we will do? So E0 is your minimum weight edge. Then what? Like in this example, 13 is your minimum weight edge, E0. Where will you, what is the cut here that you should be interested in? Exactly. So the cut is, A is the red vertices and A complement are the orange vertices, which are, so these are A is the covered vertices, A complement is uncovered vertices or yet to be covered vertices. And then you have to, so this gives you a way of abstraction. So now you can step back and think about edges that go across red to orange. So red to orange, you can see these edges, right? 33, 50, 30, and 44. So the question is, which one of these should you pick? Sorry? Yeah, so again, you should pick the minimum amongst these, right? So that is lemma 2. So you have a strategy and now you have to prove it. So the min weight edge in the cut E comma E complement is in MST. Is in fact every MST. So this is a bit stronger. For all A. So this is actually stronger than what we wanted. Irrespective of what subset you are looking at, irrespective of what A you pick, when you think of the cut, the min weight edge in the cut will always be in MST. Okay, so this is a very strong statement, stronger than what we needed. Is it clear? The statement is clear? And the way we will apply it in the final algorithm is what I already described, that A you will take as the red, the covered vertices in that example, and complement will be the orange vertices, and then you will just pick the minimum there. Now, its proof is what we have to give. So how do you prove this? Why is which edge amongst these edges, cut edges, is the most important? So we are claiming that if these are the 3 cut edges, then 9 is the most important. 9 is there in every MST. Right? So why is that? We want to show that 9 is in every MST. So let's consider an MST T prime without E1, where E1 is the min weight edge of cut. Okay, so the proof will be essentially by contradiction. So say you don't pick 9, there is some MST which doesn't pick 9, which is the min weight edge, we call it E1. So now what we will do is that we will transform it and get a smaller MST, which will be a contradiction. So how do you show that? Just schematically show it. So inside A you have edges. No. Our graph is a connected graph. There is only one connected component. Okay, yeah, then A, if you remove all the cut edges, then the graph is cut into 2 connected components. This is the meaning of cut, yes. No. So that is what will happen in the algorithm, but the lemma here is saying something stronger. It is saying that every MST will contain this 9, irrespective of what algorithm or strategy you use. This is a mathematical statement. It's a property of graphs that in a cut the minimum edge has to be used. Otherwise your tree is not MST. You can do something better. So how do you do better is what we will now show in the proof by contradiction. So there are these paths which we don't care about inside A. and inside A complement. These are the orange paths, orange edges, sorry. And E1 is, let's say you picked 10 instead of 9 in your MST T prime. So suppose an MST made this choice. Okay, sorry, this is not E1. Let me call it something else, E prime. And this is 9, this is E1. So there is this T prime is using this. So this is T prime. So what I'm showing in this figure is that T prime uses, it's a spanning tree, and it is using an edge from the cut E prime instead of the one which I wanted to be used, which is the minimum, that's E1. Let me add MST T prime without E1. And moreover, E prime is the one that it is using from the cut. Say T prime uses E prime from the cut. So from the cut, something has to be used, right? Because is it possible that MST T prime, for example, T prime does not use any edge from the cut? That isn't possible because of the discussion we had before, that if that was the case, then you have two different connected components. But spanning tree is supposed to be connected, right? So some red edge through the cut, in the cut has to be used, but it's not E1. So let's say it's E prime, which has a higher weight. So in that tree, now let us add E1, which gives a cycle. So introducing E1 in T prime creates a cycle which implies, now since it's a cycle, well, okay, so the cycle uses both E prime and E1, so I just need that. Creates a cycle using both E prime and E1, both from the cut. Okay, so these two edges from the cut are being used, and there is a cycle. How do you break the cycle? Just remove one, right? So the E prime, which is the bad one, remove it. So the cycle breaks and you get a different spanning tree. So delete E prime to get spanning tree T, which is T prime, removal of union E1, and then removing E prime. Right, so you understand the weight of this. Weight of T is equal to weight of T prime plus E1 minus E prime, which is what? Yeah, so weight of T is smaller. So this means that weight of T is strictly less than weight of T prime, which means, well, T prime we assume to be an MST, and we are getting a spanning tree which is even smaller. So that's a contradiction. So this is a contradiction to T prime being MST. Okay, so this can't happen, which means that we made somewhere a wrong assumption, which was, the wrong assumption was that some MST T prime can escape E1, can avoid E1, right? So that's the mistake. So this means that for all MST T prime, E1 is contained. Right, so this proves our lemma. Every MST contains the edge E1, which is defined by definition the smallest edge in the cut. Right, so this lemma, the proof of the lemma is pretty general. It is not using any algorithm. It is just telling you a property of cuts and MST. This is a very powerful property. Any questions? Yes. Where did we assume that? I mean, okay, the graph, overall the graph is connected, so whether A is connected, that we don't know. A or A complement may be internally disconnected, because you might have to go from A to A complement and come back for connection. So, I mean, for example, this could have been a bipartite graph also. So then A and A complement are internally completely disconnected. Right. So in the bipartite case, how will the spanning tree look? So we should think about that. When A is disconnected. In fact, A has no edge. So A and respectively A bar, they have no edges inside. So that is a good question. You should draw that picture and think about it, how the proof is behaving in that case. Okay, so once this is done, we will, was there an idea 0? Yeah, so that's now our next idea is this very clever idea using these lemmas, which is that you, of course, start with the min weight edge in the graph, and then to grow that slowly towards iteratively towards an MST, you look at the cut and pick the min weight in the cut, right, and then repeat. So pick min weight edge E0, let's say vertices are U0, V0. And that gives you idea of the cut. So now the cut definition should be with respect to this. So the vertices that are covered versus A complement which are uncovered. And there you pick minimum weight edge to proceed. E1, which is, let's say, U1, V1 vertices in the cut now. Right, so these two are different steps. So first step was happening min weight in the graph. And then to proceed, the second choice is in the cut. And how will you grow the cut? How will you grow the cut or change the cut now? So A will now grow. Sorry? In A, yeah. So A will grow now. So you will change A to bigger. And so on. Right, so now you will be working in every step you are working with the cut. The set A grows, E complement shrinks, and look at the cut edges and pick the min there. So that's essentially your pseudocode. So we call this pseudocode MST cut. Given graph and the weight function, edge weight function. So the tree initially is empty, and we start. What is the A that we start with? Sorry, empty. Yeah, empty is how we have described before. But interestingly, you can actually start with any vertex also. So let me do that version. Just V is arbitrary, just pick any vertex. So the thing is that this lemma 2 is so strong that now you can ignore lemma 1. You can forget it. So now you can just work with lemma 2 here, which is even more clever. So you take an arbitrary vertex V, make that red, and look at the cut. In the cut, you pick the min weight edge, grow A, and grow the tree. Okay, so this is what the pseudocode will do. So while E is not everything, you have work to do. So what you do is compute min weight edge x comma y in. So by lemma 2, use the cut. And so this edge when you pick, then you have covered potentially these two vertices. So let's add them in the tree. And how do you change A? How does the cut change? No, so x is already in A, so y is the new thing. So just add y. And that's it. So so this thing repeats, A gets bigger, A complement gets smaller, ultimately A is everything. And when A is everything, then your T is the MST. So you return that. Is that clear? Yeah, so lemma 1 is not needed. You don't need to pick the minimum weightage in the graph. So we will not actually use this. So let us skip this part. And we just use the cut property. Okay, so this is the MST using cut. Any questions here? This again, due to greedy algorithm, it's very simple. Right? This paradigm gives you very simple algorithms, but very tricky proofs. Even to come up with the greedy parameter requires a lot of creativity. So what is the complexity of this? How many while iterations? N many, worst case. And what is the cost of single iteration of while? Yeah, that also you cannot say anything. In worst case, it can be N because the cut has, unfortunately, it can even be more than N. It can be just M. Because in the cut, there are M edges in the worst case. M can be much bigger than N. M can be N square, order N square. So N iterations, each time M. So, yeah, I think we're getting closer to the end. So MST cut finds MST in N times order M. So M in time. Right, which in general could be kind of quadratic. So input size is around M and this is M times N. So this is quadratic time algorithm. Can you make this faster? Just like we did in the previous class, can you do it faster by a heap implementation? So what do? So when you do it faster, then it becomes the algorithm by Jarnik and Prim. So this is called Prim's algorithm usually, but Jarnik had given the main ideas already before. So this Jarnik-Prim's algorithm says that MST can be found in M log n time. How? How do you replace n by log n? So you want to compute min weight edge. So it makes sense to implement or store the edges with weighted edges in a min heap. Right? So let's do that first. So store the weights of the edges as min heap. Let me just call it heap. But will this be enough? um, because you have to compute the smallest edge in the cut, not overall. How will you do that? So the trick here is that the vertices which are covered, which are in T, you delete all the edges which are incident on them. So you do deletion in the heap also. So as T grows, delete extra edges. Leave the extra edges incident on these new X and Y. Okay, so this is what we will do. We'll keep removing these extra edges, and that will save our time. So ultimately, you will get it takes time per edge. It will take log m. You have to do a global analysis of the pseudocode. So there are only m edges, and they are reducing. And per edge, the cost is only log m. So this is less than equal to order m log n. Is that clear?